So, hello, KS. I hope I'm audible. So, maybe I'll just start in like 2-3 minutes so that a few more people can join the meeting. So, I think we'll start at like 6-5 so that some more people can join. So, I guess no one else is joined till now. So, I think we'll start the session as right now. So, first of all, let me just introduce myself like every session. So, hello everyone, whoever is watching on YouTube also. So, I'm Lakshay Saggi, the discrete mathematics TA, the discrete math NPTEL course problem solving TA for the Tuesday session. So in this is I think session 9. So in this session, we'll discuss problems related to like inclusion exclusion principle. So like this is some inclusion exclusion principle can sometimes get a bit complicated. So like in these problems, I'll advise you to pay a bit more attention and like ask if something is not clear right away, because this is a very important sort of topic, and like there are a lot of ways in which people can make mistakes in this topic. So yeah, just pointing it out that whenever you get if you feel any doubt like in any concept in the problems I'll be discussing, so just ask right away. So yeah. So I'll just share my screen and we'll start with the problems. So let me just share my screen. Okay, so I hope my screen is visible. So Aditya or KS, can you let me know via thumbs up or in chat if it is visible? Okay, okay, it's visible. Thanks. So let's just start with the first question right away. So uh, first of all, what is inclusion and exclusion principle? I'll just maybe write down the basic to like remind you guys of the definition of inclusion exclusion principle. So principle of inclusion exclusion. I think like I just write it for three sets. Suppose there are three sets. Suppose there are three sets A, comma B, comma C. Uh, uh, if you want to write, let's say the value of, let's say the cardinality of A union B union C, like this mod symbol, like this mod, like A union B union C is a set, and this mod symbol denotes the cardinality of that set. So some people prefer to write it as like n of A union B union C, which means like number of elements in A union B union C. But I like to refer to it. I generally denote it as like a modulus. And so this can be written as uh, number of elements in set A plus number of elements in set B plus number of elements in set C minus number of elements in set A. A intersection B minus B intersection C minus intersection A, and then we add back. So this is so, and then we add back basically A intersection B intersection C intersection B intersection C. So this is the principal inclusion exclusion. It's just like for three sets it's this, and you can generalize it for like n sets also. So what it says is basically like union of A, B, and C is nothing but just like number of elements of A plus B plus C. And now what elements we have double counted? We have double counted the elements which are in A intersection B, B intersection C, and C intersection A. So we try to subtract them. But while subtracting them, we have doubly subtracted these much elements, the A intersection B intersection C elements. So we just add them back. So this is the principle of inclusion exclusion. Fairly simple. Like you can just draw the Venn diagram and verify that this is the case. So it's not too difficult to see that this will be the case. And this is something which we have done in high school also, if I remember correctly. But its applications can be extended to like various examples. So I guess we'll just start with the problems now. So you can see its applications also. You must have seen some applications in the lectures also, but yeah, in this session also we'll be discussing some of them. So first question is, how many positive integers between 1 and 1000, including both 1 and 1000, are not divisible by 3, 5, and 7? So just to get an intuitive idea of the problem, so what we need is we are given a set of numbers like from 1 to 1000. So a set of 1000 numbers. And from that set, we want such numbers which are not divisible by either 3, 5, or 7. So what we actually want is if we take like, let's say three sets which are like that set of numbers which are divisible by 3, one set which is divisible by 3, one is divisible by 7, and one is divisible by 5. Then what we want is the basically the intersection of negations of these sets. So basically what you want is the number of elements which are not divisible by 3, 5, and 7, all of these. So this is what you want. So this can be obtained intuitively by like similar arguments as we use in the principle of like inclusion exclusion. So before that, let's just introduce, I guess, some notation. Yeah. So maybe let's just say like n of A, comma B, comma C, and so on. Like for here, we have only like 3, 5, and 7. So maybe I'll just write it like this. So I'll just denote, this is just a notation. Let me clear this problem. And by n of a, I'll denote uh, number of elements between 1 and 1000 are not, which are divisible, which are divisible by a, like which are divisible by the number a. And similarly, if I write like, let's say n of a comma b, then by this I mean number of elements between 1 and 1000 which are divisible by both a and b. Why am I breaking down, like I actually need to find the numbers which are not divisible by like 3, 5, and 7. But I'm breaking down this into like number of elements which are actually divisible by, let's say a is 3, which are actually divisible by 3, which are actually divisible by 3 and 5. So I'm sort of trying to break this down in this sense because uh, it's easier to calculate like the numbers which are divisible by 3 between 1 and 1000. For that, we can just do 1000 by 3 and take like its greatest integer function, and that will be the value. But the numbers which are not divisible by 3 and 5, it's a bit more complicated. So we try to reduce that to the values which we can actually calculate straightforward. So I hope I'm being clear. Similarly, like n of a comma b comma c is nothing but n of a comma b comma c will be like similar definition. Just like I just extended to divisible by a, b, and c. Dots are because like number of elements between 1 and 1000, which are divisible by a, b, and c. Maybe I just copy this. So this is the notation I'll try to use. So now what we need to find is uh, the numbers which are not divisible by 3, 5, and 7. So how can I write this set as? So uh, okay. So what do I want is like n of 3 will be the set of elements or like number of elements between 1000 which are divisible by 3, and number of elements which are divisible by 5 which are divisible by 7. So maybe we'll just replace this. Okay, maybe I'll just write it this way. So by inclusion, maybe I'll just write it uh, like this. So number of elements not divisible by 3, 5, 7 is equals to. So what will this be equals to by principle of inclusion exclusion? You can see, I just like to see it in this way that suppose we were given like total numbers which was like 1000, and from 1000 I subtract the, basically what I want is the number of elements which are not divisible by 3, 5, and 7. So how I view the principle of inclusion exclusion for like faster applications. Okay, Aditya, you have written answer 457, but I'll just explain the how we arrive at this answer also. Your answer is correct. So, so I'm just trying to tell you guys how I like to see principle of inclusion exclusion so that we can answer it faster. So I want number of elements not divisible by 3, 5, and 7. So what do I want from total number of elements? I'll sort of try to delete the elements which are divisible by 3, which are divisible by 5, and which are divisible by 7. So I'll just do that. So first of all, we were given total 1000 numbers. So from that, I remove the elements which were divisible by 3. Then I remove the elements which were divisible by 5. And then I remove the elements which were divisible by 7. But while doing this step, I would have reduced the numbers which were divisible by 3 and 5 twice. Similarly, the numbers which are divisible by 5 and 7 twice, and similarly 3 and 7 twice. So I'll just add those values back up. So now I'll just add back. This is not equals to, this is a plus sign, sorry. Then I'll add back n of 3 comma 5, and plus I'll be adding back n of 5 comma 7, and similarly I'll be adding back n of 3 comma 7. I hope you get the drift of it, why I'm doing it this way. This is nothing but till now what I have done is from total numbers I have subtracted numbers that is by 3, 5, and 7. And since I subtracted some numbers twice, I'm just adding these numbers back up. But while doing this, I would have this is like you can just remember this sort of trick. So you can apply the principle of inclusion-exclusion directly without writing it down in the set notation and doing that sort of thing. Maybe you can bypass it for faster calculation. So, and while doing this, what I would have done is I would have added the numbers like which were divisible by like with the sets which were like the numbers which are divisible by 3, 5, and 7. All of these I would have added that set twice. So I will just remove that set. Now 3, 5, 7. Uh, this is something which you can verify like by writing down the sets and like and using principle of inclusion exclusion like this. But maybe you can just directly write down the calculations like this. Like you can view it as like deleting numbers equal by 3, 5, and 7. And while doing this, I would have like subtracted these numbers twice. So I'll add them back up. And while adding them back up, I would have added these numbers like twice. So I need to subtract them once. So this will be my final answer. So this will come out to be so 1000 minus, so n of 3 will be, n of 3 is nothing but number of elements between 1 and 1000 which are divisible by 3. So n of 3 will be like 1000 by 3, which will be like 333. We take the lowest integer function for that. Similarly, for n of 5, I'll get 200, 1000 by 5. And for n of 7, I'll get 142, I think. Yeah. And then while adding back up, I'll get like I'll be getting like 1000 by 15 will be 66. And then like basically what I need is numbers which are divisible by 3 and 5. So which are divisible by 3 and 5 will be just the numbers which are divisible by 15, since 3 and 5 are like co-prime. Otherwise, like suppose this was like numbers divisible by like the numbers which are not co-prime, like 6 and 9. Suppose the we obtained instead a value which was n6 comma 9. In that case, I would not. In that case, I would have to do it by LCM of 6 comma 9. I hope you guys get the drift of what I'm saying. So what I'm basically saying is like suppose to calculate this number n of a comma b, with the number of elements 1 and 1000 which are divisible by a and b. So this value will be equals to nothing but like 1000 divided by LCM of a and b. Not you can't just directly write the product of a and b. This will be actually equal to the 1000 divided by LCM of a and b. So if a and b are co-prime, then their LCM is like a into b only. So that's why here like LCM of 3 and 5 will be 15 only. So I can just write like 1000 by 15. Otherwise, if the numbers were not co-prime, suppose the numbers were instead 6 and 9. In that case, I'll have to divide it by like LCM of 6 and 9, which is 18. So numbers between 1 and 1000 which are divisible by 6 and 9 will be equals to like 1000 by 18 and not like 1000 by 6 into 9. So just keep that sort of small thing in mind. I'm sure you guys must already know this, but just putting it out there. So if someone is confused, then they can refer to this. So similarly, this n5 comma 7 will give me 1000 by 35, which will I think will come out 28. And similarly, this n3 comma 7 will give 1000 by 21, which will come out to 47. And now while adding these numbers, I now need to subtract this n3 comma 5 comma 7. So 3 into 5 into 7 will be 15 times 7, which will be 105. So this will come out to like 1000 by 105, which will be equals to 9. So while doing this calculation, this will give us like 1000 minus 333 minus 200 minus 142 plus this. So I have a calculator, so this just gives us 457. Just putting in the calculator, this gives us 457. So this is the correct answer. So yeah, Aditya had written in the chat the answer as 457. So yeah, Aditya, your answer was correct. Nice one. So I just underline the answer and maybe I'll just write the answer in next line also. Teachers. So I hope it's clear to you guys how I wrote this expression directly. Uh, this expression, like I just gave you the intuition behind it. It's same as principle of inclusion exclusion, but it's just like bypassing one step of writing it explicitly in form of sets and doing it, and instead directly writing it out, which can be helpful in a lot of scenarios since uh, it's bypassing one step, so it can be done faster. So it's just like I just provide the intuition behind principal inclusion exclusion. Here the like this can be seen as a formula, but this can also be seen intuitively. Why is this? So while adding this, I have added this extra, this extra, this extra, and while subtracting this extra, I subtracted this much extra. So yeah. So I hope it's clear. So we can move on to the next question. So next question says, how many onto functions are possible from a set of 9 elements to a set of 4 elements? So I'm sure you guys must have done this sort of thing in lecture also, but I'll just try to do this in a similar manner as I did it here. So what do we need to do is what is an onto function? An onto function is a function in which like uh, what is every element of the codomain is mapped, like codomain equals to range. In that case, it's an onto function. So here the size of codomain is 4. So I'll need those functions which have a range of 4. So what I need is these 4 elements, and each of these 4 elements should have at least one pre-image amongst these 9 elements, right, guys? So for this, how can we do it is total number of onto functions. Okay, need to find total number of onto function. So what can I do in this case is we know the total number of functions, right? So total number of functions will be like each of these 9 elements has these 4 choices to be mapped. So there are 9 elements in the domain and there are 4 elements in the codomain. So actual total number of functions will be, maybe I'll just write it first. Total number of functions is equals to, so each of these 9 elements has 4 choices. So it will be 4 to the power 9, right? But what I want is actually the number of onto functions. So for onto functions, what I need is uh, just in a similar manner as I did here, I'll be doing the calculations here also. So I have this total number of functions 4 to the 9, but there will be some functions where one of these 4 elements will not be mapped, right? So we need to remove those cases. So these are 4 elements. So choosing one of the elements to not be mapped can be done in 4C1 ways. So in 4C1 ways, there will be one element which is not mapped. And when that element is not mapped, these 9 elements can then be mapped to, let's say, the remaining 3 elements. So each of these 9 elements will now have only 3 choices. So this will come out to, so 3 to the power 9. And now while doing this, while subtracting this from total number of functions, while subtracting this amount, what I have done is, suppose there were these four elements were E1, E2, E3, E4. So once I have from this total number, I subtracted a number of elements corresponding to when E1 is not mapped, and one time I have subtracted when E2 is not mapped. So I have subtracted those cases twice in which E1 and E2 both are not mapped. Right? I hope you guys understand what I'm saying. So basically, I subtracted those cases extra in which like two elements are not mapped exactly. So I'll try to add those cases back up. So the two elements which have not been mapped can be chosen in 4C2 ways. So it will be nothing but 4C2 times. And now since two elements are not mapped, so only two elements can be mapped. Since suppose E1 and E2 are not mapped, then these nine elements can go to like E3 and E4 only. So there are two choices only for each of these nine elements. So this will be 2 to the power 9. And now while doing this, again, like I said here, like I subtracted 357, then I add back 355737, and then I'll have to subtract this 357, these triplets, because I would have subtracted them, added them extra. So here also I would have added the like triplets extra, like suppose the elements. So I would have added that case extra where like E1, E2, E3, all of these are not mapped. So just referring it out there, this is our total number of functions. These corresponds to when E1 is not mapped, when E2 is not mapped, E3 is not mapped, E4 is not mapped. And while doing this, I would have and subtracted some extra, which I add back by pairwise additions. And now I'll need to subtract the triplets again, since I would have added them extra amount. So this will come out to like 4C3 ways. E1, suppose E1, E2, E3 were not mapped. So now only E4 can be mapped. So there will be only one choice for each of these nine elements. So this will come out to like 1 to the power 9. So this will be the answer. So like an additional amount will also come, which will be like so while adding like subtracting all of these, I would have subtracted the case where all of those were not mapped. So like while subtracting this, I would have subtracted extra the case where E1, E2, E3, E4, all of these were not mapped. So that will be nothing but like 4C4. But if E1, E2, E3, E4, all of these are not mapped, then these elements cannot be mapped to anything. So its corresponding coefficient will be nothing but a 0. So that's why I just skipped this term early. So this will be the answer. So this will just come out to 0 only. So I hope you guys understand what I'm doing here. Nothing but like total elements minus when the case E1 is not there, plus the case E1 and E2 are not there, minus the case E1, E2, E3 are not there. Like last term is irrelevant. This will be the final answer. So I hope it's clear to you guys, since as I said earlier, it's this sort of counting principle is something I'll be using in all of the questions. So there are 10 questions. I'm still at second question. So if you guys have doubt, maybe you can ask in chat so I can explain it again. But this will be the core of our calculations. Like this is how we'll be doing everything. So maybe you guys can do the calculations by yourself. I just happen to have the answer for this. So answer is 186,480. But I hope the how we did the calculations is clear to you. So, principle like inclusion exclusion is nothing to answer. It's just straightforward, like set theory, and like you can do this using Venn diagrams also. But it's just a nice explicit way of putting everything together. So that's why we have named it something like we have named it as a principle, and we just like otherwise it's nothing but like basic set theory. So yeah. So this question was done. So now let's come to the third question. So third question says that in how many ways can integers from 1 to 10 be arranged such that no prime number is as it is at its natural place? So for this, first of all, let's try to see like it's asking and how many ways integers from 1 to 10 be arranged so that no prime number is at natural place. So it's dealing with first of all prime numbers between 1 to 10. So it's better to list out these numbers. So prime numbers between 1 to 10. So 1 to 10 means both 1 and 10 are included. Although these both are not prime, but still. Some notation which is from which says integers from A to B means the range also includes the endpoints, like A and B both are also included. So just keep that in mind. So like here in integers between 1 and 1000, it's explicitly said, including both 1 and 1000. But if it does not say like here it does not say whether 1 and 10 are included or not. But by default, you can assume that both endpoints are included. So yeah. So prime numbers between 1 to 10 are 2, 3, 5, and 7. Right? So these are the only prime numbers between 1 to 10. So what we want is the number of ways in which like no prime number is at its natural place. So 2 should not be at second place, 3 should not be at third place, 5 should not be at fifth place, and 7 should not be at seventh place. And I just need number of permutations which do something like this. Right. And other numbers can be anywhere. I don't care. So again, doing this. Yeah. So how I do it is first of all, let's just write down the total number of permutations. Total number of permutations. What will be the total number of permutations? It will be nothing but total number of actual permutations will be like 10 factorial, right? Since there are 10 numbers and they can be arranged in 10 factorial ways. So actual total number of permutations will be 10 factorial. And now, or maybe I'll just say total number of arrangements since it's asking arranged. So this will be 10 factorial only, and number of arrangements such that no prime number is at its natural place. This will be equals to, we'll write this equality next line. This will be nothing but like, let's say 10 factorial. This is the total number of arrangements minus what I'll be subtracting is something like which I've already discussed with you guys. So from total number of ways, what I'll do is I want no prime number to be at its natural place, right? So first of all, what I'll do is I don't want two to be at second place, 3 to be at third place, 5 to be at fifth place, and 7 to be at seventh place. So I'll do it piece by piece. So from total number of ways, I'll first subtract like the number of ways in which 2 is actually at its natural place. So minus uh, ways in which 2 is at second place. Or maybe I'll just write on the formula only. Yeah. From this 10 factorial, what I'll subtract is first of all the case where 2 is at its. Maybe I can put it down in this sort of notation so it's easier for you guys to follow. Bear with me, guys, just a minute. So again, I'll be following some sort of this sort of notation only. So notation is in which is at eighth place. So n of a will denote like 1 second, guys. Just writing down the notation, and I'll just make clear to you guys what does the notation mean. So n of a, so I just introduced a notation like I did in the first question, because writing it down in form notations makes it a bit easier for me, as well as for me to write it down and for you guys to understand it. So you guys can abstract this. So n of a just is nothing but number of ways in which the number a is a number of permutations, maybe number of arrangements of these numbers 1 to 10 such that a is at ath place. Similarly, like this n of a comma b will be nothing but number of arrangements in which a is at ath place and b at bth place. So like if we like put n of 2 will be nothing but number of arrangements in which 2 is at second place. And like n of 2 comma 3 will be number of arrangements in which 2 is at second place and 3 is at third place. So this sort of number can be like easily computed. And how can this be easy computed? Maybe I'll just come back to that later. So now what I want is, so this is something, and like this notation can be continued to like n a comma b comma c up to like, let's say like something d e f g h. So it will be nothing but number of arrangements in which a is at ath place, b is at bth place, c is at cth place, and so on. So now what I want is number of arrangements such that no prime number is at its natural place. So what I want is the number of arrangements in which 2 is not at second place, uh, 3 is not at third place, 5 is not at fifth place, and 7 is not at seventh place. So I'll just piece by piece subtract these guys. So from total number of ways, I don't want 2 to be at its natural place. So n of 2 will be nothing but in which 2 is at second place. So this will, when this is subtract, n of 2 is subtracted from 10 factorial, it will give me the number of ways in which 2 is not at second place. Similarly, I'll subtract n of 3 also, such that 3 is not. Similarly, I'll subtract like n of 5 and n of 7. And while subtracting these, I would have add these terms extra. So these will be n of 2 comma 3 plus n of 3 comma 5 plus n of. So maybe okay, I think I can write it down explicitly for first for this question, but maybe for later questions I'll not write it down explicitly. There will be like, since there are 4C2 ways of like finding a pair of two, so there will be like 4C2 6 terms. So 2, 3, 3, 5, 5, 7. Then one term will be 2, 5. And it will be 2, 7. And then what term is remaining? 3, 7 is remaining, right? Keyboard is doing something weird today. Intend to write, and what I am actually typing out is coming out a bit different. So yeah, so from 10 factorial, what I've just subtracted are like individual terms and then added these pairwise terms back. And then I'll be subtracting the triplets again, since I would have added them more times. So 2, 3, 4, then n of, sorry, 2, 3, 5, and n of 2, 3, 7. There will be like 4 triplets because 4C3 is 4. Then a triplet will be n of 2, 5, 7 minus n of another triplet will be 3, 5, 7. I hope it's clear to you guys. So say there will be these 4 triplets, and then I'll just be adding back the fourths, the quadrates basically. So quadrates will be 5, 7. So this will be my answer. And why is this the answer? As I earlier said, also the intuition for principal inclusion exclusion. By subtracting individually, I have like added these pairwise terms, subtracted these more, so I just add them back. And while adding them back, I have added some things extra, which will be this amount. And while subtracting this amount, I would have subtracted something extra, which will be this amount. So I just add that, add it back up, and I'll obtain my answer. So why I have done it in this way using why we have done this in using principle of inclusion exclusion. Again, the intuition is that these numbers like n of a number of elements in which a is at a's place, these numbers are easier to calculate. But this number, like there is no straightforward way of calculating this number, like in which no prime number is at its natural place. You can calculate number of ways in which a prime number is at its natural place, but the number of ways in which no prime number is at its natural place, this number is a bit more difficult to find. So that's why we use principle inclusion exclusion for this way, for this. So here, this will be nothing but like 10 factorial minus. And one thing to note is that all these values like n2, n of 3, n of 5, n of 7, what does this mean? Like n of 5 means nothing but number of ways in which 5 is not, in which 5 is at fifth place. So what does this mean? There were 10 numbers originally and 5 is fixed to be at fifth place. And now the remaining positions are 1, 2, 3, 4 and 6, 7, 8, 9, 10. And the remaining, there are remaining 9 numbers. So they can be arranged in any number of, in any order in the remaining places. The only thing which has been fixed is 5 has to be at fifth place and every other number can be in any other manner. So that's why like if we have fixed 5 to be at fifth position, then there are only 9 remaining positions and 9 remaining numbers. And since they can be like put in any position, so this will come out to like 9 factorial. Like, because 5 is fixed to be at fifth position. So n of 5 will come out to 9 factorial. Similarly, n of 7 will also be 9 factorial because 7 is fixed at 7th position and remaining numbers can be. And similarly, these numbers are also at 9 factorial and this is also 9 factorial. So just to put it explicitly, so basically what I mean by this is, so like suppose there was like similarly n of a comma b. In n of a comma b, what do we mean? By n of a comma b, we mean a is at ath place and b is at bth place. So this means a and b's positions are fixed. So the remaining 8 numbers, since there were total 10 numbers, 2 positions are fixed. Remaining 8 numbers can be put in any number of any order. So there will be 8 factorial ways of putting them. So n of a comma b will always be equal to 8 factorial regardless of values of a and b. Similarly, n of a will be equal to 9 factorial. N of a comma b comma c will be like 7 factorial and so on, regardless of values of a, b, and c and so on. Okay, so one easier way to write it down is nothing but, so what do we need? So there is these 4 numbers and in this subtraction, which we have just uh, selected one number out of these 4. And then we have you like the value of that is like n of 2 is 9 factorial. So I can just write it down as like selecting in 4c1 ways one of those numbers. And then the value is nothing but 9 factorial. Uh, like this whole part can be written as like 4c1 times 9 factorial. And similarly, while selecting a pair, like selecting a pair can be done in 4c2 ways. 4c2 is 6, as I had mentioned. So there are these 6 ways. So this will be like 4c2 times, and the value for each pair will be 8 factorial, as I mentioned, since like a is at ath place, b is at bth place, so remaining 8 numbers now can be moved freely. So each of these values will be 8 factorial. So 8 factorial. So why I just wrote down the expanded form to show you guys how these like 4c1, 4c2 coefficients are actually coming. So 4c1 coefficient is coming because there are like these 4 numbers. Similarly, 4c2 coefficient is because these are 6 pairwise numbers. And similarly, I'll get 4c3 from these triplets minus 3 times. Now 3 numbers are fixed, like let's say 2, 3, and 5 are fixed. So there are remaining 7 numbers which can be put in any order. So this will come out to 7 factorial ways. And now, sorry, the last will be like 4c4 times 4c4 times like this number. Like 4c4 is 1 only, so that's why there is only one number of this quartet type. And this is nothing but like 2 is at second place, 3 is at third place, 5 fifth, and 7 7. So 4 numbers are fixed. So 6 numbers are free to move. So this will be like this remaining 6 numbers can move in 6 factorial. So yeah, this will be answer for this question. So I don't know the actual answer what will come out, but the calculation is this only. So I'll just maybe underline this. You guys can calculate it yourself also, which I don't think is, maybe I just not underline since it's a bit confusing. The actual value. You can put it on calculator or anything, but this is the correct answer. 10 factorial minus 4c19 factorial plus 4c28 and 4c7 plus 4c4 6 factorial. And I hope it's clear to you guys how this answer came about. So yeah. Now let's go to the fourth question then. So fourth question is, okay, I'll just put it in new page. Just says that in a 3x3 chessboard, which of the following statements uh, are true? So one rook can be placed in 9 ways. So there is a 3x3 chessboard, and which of the following statements are true? So one rook can be placed in 9 ways. Maybe I'll just put it on state by statement. And one says that one rook can be placed in 9 ways. So since there is in the chessboard is 3x3, so there are 9 squares to place the rook. So yeah, so like there are only 9 boxes in which rook can be placed. So it is correct. There are only 9 squares in the board. Now statement 2 says, so statement 2 says two rooks can be placed in 92 ways such that they do not kill each other. So what is actually 92? You can see like there were 9 squares and it's selecting, and 92 just means like selecting 2 squares out of those 9 squares. The 3x3 chessboard has 9 squares. So it's just selecting any 2 squares of that chessboard and placing the 2 rooks on it. So is this correct number of ways? Because it's also in the number of ways, the restriction is that the rooks should not kill each other, right? Such that they do not kill each other. But if I just select any 2 arbitrary squares in the 3x3 chessboard, then it's possible, right? That the 2 rooks will be killing each other. Suppose both the rooks are in first column only, are placed in 2 boxes, like first column, first row, and one second rook is placed as first column, second row. So those two rooks can kill each other. So if this 92 bound is not correct, we'll need to subtract some ways in which we need to subtract some ways so that rooks can actually so that rooks do not kill each other. So this is something I think this has been covered in the lectures already, like the correct how to calculate it correctly, the number of ways, the rooks polynomial and stuff like that. So I'll not get into the actual number of ways, but yeah, this 92 is definitely incorrect because correct as we are selecting any 2 arbitrary squares out of the 9 squares chessboard, but these might belong to the same row or column. That's why statement 2 is incorrect. I hope you guys get the reasoning for this. So now let's go to statement 3. He says that 3 rooks can be placed in 6 ways such that they do not kill each other. So there is a 3x3 chessboard and 3 rooks. We need to place 3 rooks. So this is nothing but basically we just need to find a permutation of 3 numbers, and like correspond to every permutation, there will be a way to place the rooks. This must have been covered in lectures. So this comes out to 3 factorial, which is actually 6. So this statement is correct. As rooks can be placed in 3 factorial, which is equals to 6 ways. So correct answer is 1 and 3 are correct. So yeah, statement 1 was correct, statement 3 was correct, 2 was incorrect. So yeah. Let's come to this fifth question. Fifth question is a bit trickier. So what does this say? It just says how many integer solutions are there for the equation x plus y plus z is 18, where x is less than 5, y is less than 9, and z is less than 7, right? So for this question, first of all, let's just say there were no restrictions given to us. Like suppose this part was not there. So which we just want to find out how many integer solutions are there for the equation x plus y plus z is 18. So for this, I think we already know the answer from like the generating functions class and like that. So for this, the answer comes out to, I guess, 20C2. I think, yeah, the answer will come out to something like 20C18. Yeah, because like there are 3 numbers and 18 of these. So 18 plus 3 minus 1, C18 is really 20C18 or 20C2. So yeah. So first of all, what's the total number of solutions? Nothing but plus 3 minus 1 C18. So, which is nothing but 20C2 or 20C18, whatever you can write. But we need to find the integer solutions where x is less than 5, y is less than 9, and z is less than 7. So solutions where x less than 5, uh, y less than 9, and z less than 7 is nothing but maybe I can write this here. It's nothing but like a total number of solutions, which is 20C2. So first of all, I've calculated these 20C2 solutions. And now, like as the similar as the argument which were done earlier, also I'll be doing same sort of arguments here. So total number of solutions are 20C2. And now I only want the solutions where x is less than 5, y is less than 9, and z is less than 7. So what type of solutions do I need to subtract from this? Like these 20C2 solutions. So from this, these are the total number of solutions. So from this, I need to subtract the solutions of the type where x is greater than equals to 5, because I actually want only those solutions where x is less than 5. So I need to subtract the solutions where x is greater than equals to 5, right? Similarly, I need to subtract the solutions where y is greater than equal to 9 and solutions where z is greater than equals to 7. So this will come out to nothing but. So first of all, I'll subtract like from this 20C2, I'll subtract the number of ways in which number of solutions in which x is greater than equals to 5. So this n of this will just denote the like the number of, you can read it as like number of solutions where x is greater than equals to 5. Similarly, I'll need to subtract those solutions where y is greater than equals to 9. Because I need y to be less than 9. And similarly, I'll need to subtract the solutions where z is greater than equals to 7. While subtracting these, I might subtract the solutions where these two conditions, let's say, are met together. So I need to add those conditions back up. So I'll just add plus n of like x is greater than equals to 5. I just do it in another line because n of x is greater than equals to 5, comma, y is greater than equals to 9. So this you can read it as the number of solutions in which both of these conditions hold true. So like I defined something like this here also, n of a comma b is nothing but like where a's condition also holds true and b's condition also holds true. So similarly here, so this just denotes the number of solutions where x is greater than equals to 5 and y is greater than equals to 9. And similarly, number of solutions where x is so so first of all, from these two pairs, I have selected one pair. Like from these two form one pair, and then these two will form one condition pair. So number of solutions where y is greater than equal to 9 and z is greater than equal to 7. I need to add that also. Y is greater than equals to 9, comma, z is greater than equals to 7. And then I'll add this remaining pair also, which is x greater than equal to 5 and z greater than equal to 7. Plus x equals to 5, comma, z greater than equals to 7. So from total number of ways, I subtracted these three types of conditions because I actually wanted the negations of these conditions to hold. And then while subtracting, I would have subtracted something extra. So I add back this something extra. And while adding back this something extra, I would have added something more than the required quantity, which will be nothing but when all of these conditions hold together, like x is greater than equal to 5, y is greater than equal to 9, and z is greater than equal to 7. So I'll need to subtract that. Maybe I'll just put it in the line. So this will be in of x greater than equals to 5. I'll just copy this. See here. Y greater than equal to 9 and z is greater than equals to 7. So just one thing notice that the alternation between signs. So total minus the conditions which are taken one at a time, then plus the conditions when taken two at a time, minus the conditions taken all together. Right. So this will be my final answer. I hope it's clear to you. So now, if it's not clear, you can ask in chat, why is this like, why does this hold? So now what we need is we have written using principle inclusion exclusion the value of the solution, right? It will be this formula. But now we also need to calculate these individual terms, right? Like we need to calculate this n x is greater than equal to 5. Uh, so KS is writing that the answer will be only one solution. So I actually don't know the answer. So let me just check. So yeah, answer is actually only one solution. Yeah, you're correct, KS. The answer is one solution. But I'll just still show you the steps for all of this. So now we need to find each of these, the value of each of these terms individually, right? Like this, all of these terms. So what we need is n of x is greater than equals to 5 means we need to find the number of solutions where value of x is greater than equals to 5. Number of solutions to x plus y plus z equals 18 such that x is greater than equals to 5. Right. So I think this has already been discussed. What will be the value for this? So how to calculate this? What we do is, suppose we want x is greater than or equals to 5, then we can subtract 5 from both of these sides of the equation. So this part will come out to like x minus 5 plus y plus z is greater than or equals to 13. I think this sort of thing has already been discussed in the lectures, so I'll just do this orally. So it gets to be a revision for you guys, and I don't have to write it out again. So while subtract, so I need just x greater than or equals to 5. So what do I actually want? I can subtract 5 from both sides. So it will now give me x minus 5 plus y plus z is equals to 13. This 18 minus 5 will become 13. So I'll now get the equation as x minus 5 plus y plus z is equal to 13. And now this x minus 5 will be greater than or equals to 0, right? Since x is greater than or equals to 5. So whatever, so maybe we can write x minus 5 as something x prime. So I just need to find the number of solutions to the equation x prime plus y plus z is 13. And from doing that, whatever x prime I get, my actual value of x will be just x prime plus 5, since x minus 5 was equals to x prime. I hope you guys are following me. So maybe I'll just write it down. So number of solutions is that uh, x is greater than or equals to 5. So this can be done. How this can be done is take x prime is equals to x minus 5. Then we only need to find number of solutions to x prime plus y plus z is equals to 13. I just put x prime is x minus 5. So x will be just x prime plus 5. So this equation will x prime plus 5 plus y plus z is 18. And subtracting 5, I get x prime plus y plus z is 13. And this will be just nothing but for this equation, we already know how to solve this. It will be nothing but like 13 plus 2 C13, like I did here. 13 plus 2 minus 1 C13. Yeah, which will be nothing but just write it down this way. Uh, so this is equals to 13 plus 3 minus 1 C. Let's say, yeah, 13 or 2 doesn't matter. So this will be equals to 15 C13. So similarly, calculating n of y greater than equals to 9, it will come out to, you can just do this yourself also. N of y greater than equals to 9 will be just number of solutions to this such that y is greater than equal to 9. So again, what we do is instead of y, we take y prime equals to y minus 9. Here it will be 9 now. So now this side 18 becomes 18 minus 9. This will be 9 only. So for here you can check after this session also using similar steps, the solution will be now like this 18 will become instead 9 as we are subtracting 9 from both sides as y greater than equal to 9. So we just need to find the number of solutions to x plus y prime plus z is equals to 9. And this will be equals to, maybe I'll just write down number of solutions to x plus y prime plus z is equals to 9, which is equals to y prime equals y minus 9. Okay. Yeah. So if we take y prime equals y minus 9, uh, then we just want to find number of solutions to x plus y prime plus z is equals to 9. And this will be nothing but like 9 plus 3 minus 1 C2. This will be nothing but 9 plus minus 1 C9, let's say, not 2. Will be nothing but 9, 12, 11 C9. 11 C9. The better way of writing it, I think. If we take y prime as y minus 9, then n of y greater than equal to 9 is nothing but number of solutions to this equation, which is 11C9. So I just wrote it down here and for better explanation. And now for y, for this, we just get 11. It's greater than 9. And now for z, I'll just write directly. Since n is n of z greater than equals to 7. For this, I'll just get the answer as so this 18 will now instead become 11 since we need z is greater than equal to 7. So 18 minus 7 will become 11. So answer will be just 11 plus 3 minus 1 C11. So 11 plus 3 minus 1 becomes 14, 13 C11. So you can check it yourself. So this will become 13 C11. So now we want this number n is n of x greater than equals to 5 and z greater than equals to 9. So here now instead what I want is number of solutions to, like, I would take x minus 5 as x prime, y minus 9 as y prime. So I just want this time to x plus x prime plus y prime plus z is equals to, so I have subtracted 5 from here, 9 from here, so total I have subtracted 14. So 18 minus 14 becomes 4. So I hope it's clear how I write this. This is what I want. And for calculating this, I already know the answer. It's nothing but 4 plus 3, 7, minus 1, 6, 64. 64. So if you guys have any doubt in this, then you can ask how I came about this. It's similar. It's in a similar manner to like calculating this and this. This time I just introduce both x prime and y prime as I need both the conditions to hold true. So now this question can be the question which I'm discussing. Maybe you guys will feel that it's become quite boring, but I'll just write down all the terms and you can put in the values to find the data. So now I need to calculate this n of y is greater than equals to 9 and z is greater than equal to 7. So this time this will come out to x plus y prime plus z prime is equals to 18. Uh, yeah, x prime plus y prime. No, sorry, x plus y prime plus z prime is equals to 18 minus 16. Since we have 9 here and a 7 here. So it will be like x plus y prime plus z prime equals to 2. 18 minus 16 is 2. So the solution will be nothing but 2 plus 2 C2, which will be just 4 C2. I'm just doing this. You have the answer. So similarly, this value will come out to be. So this question is a very good exercise for you guys since it also involves principle of inclusion exclusion and it also involves like arguments related to generating functions and stuff like that. So yeah, I personally felt this was the best question out of this problem set. So yeah. So for this 7 plus 5 will be now 12. So this will be like number of solutions to x prime plus y plus z prime is equals to 18 minus 12, which is 6. So this will come out to like 8C6. 6. And now I have calculated all of these triplets. Now I just need to calculate this one. So this one will be nothing but I just need to find x prime plus y prime plus z prime is equals to 18 minus 7 minus 9 minus 5. So 9 plus 5 is 14 plus 7 is 21. Okay. So 16 and 5. So yeah, actually what I'll get is x prime plus y prime plus z prime is equals to 18 minus 21, which will be minus 3. So actually what I'm getting is x prime plus y prime plus z prime should be equals to a negative number, where x prime, y prime, z prime are non-negative. So this will have no solution. It's 0. So this term will be 0. So just calculating the answer now. So final answer is equals to. So I'll just, in this formula, I'll just put down all of these values which I calculated. So it will be like 20C. I'll just copy all of this formula and just substitute the values one by one. So the formula was 20C2 minus of n x is greater than equals to 5. This I calculated as 15C13. This can be replaced by 15C13. Now ny greater than equal to 9, I calculated as 11C9. So I just substitute this also. Z greater than z greater than equal to 7, I calculate as 13C11. And now maybe I'll just put all of these in same line now. X greater than equals to 5 and y greater than equals to 9 is substituted as 6C4. Y greater than equal to 9, z greater than equal to 7 is nothing but 4C2. And this x greater than equal to 5, z greater than equal to 7 is 8C6. And this last term is nothing but 0. So after calculating this, you will get the value as 1 only. So yeah, after all these calculations, complex calculations, the answer is a simple one. So yeah, So yeah, KS wrote the answer as one, and yeah, so our solution answer was correct. But like maybe for this question, you guys could have calculated it manually since these are just small numbers. Like 18 is a small integer, 5, 7, 9 are also small, so you might have just calculated the value yourself, like what can be the possible value by plugging it in. But in general, suppose if X, Y, Z were a bit larger and then like trying to find out values manually might not work. So then this is a like universal method for finding solution to this, right? Here, it doesn't matter whether it's a universal solution and doesn't matter like uh, if these values are large or small. At least I could put in this form, the combinations form. So yeah, this is the final answer. You guys can take a look at it for like a second. And if there's any doubt, you can ask me, and or I'll move just to the second question, the next question now. Okay, I guess I'll move to sixth question. So now it's a bit easier now. Sixth question is nothing but straightforward application of principle of inclusion-exclusion. So question is saying, suppose A is 10, B is 20, C is 30, A intersection B is 4, B intersection C is 5, C intersection C is 6, and all intersections are 7, then the value of A union B union C is. So it's like a very straightforward question. As I had already discussed, this is nothing but inclusion-exclusion. A union B union C is just A plus B plus C minus A intersection B, B intersection C, C intersection A plus A intersection B intersection C. This is which I discussed in the starting only, and this is what the question is asking. So maybe we can just calculate it. So you are saying KS is saying in the chart it's 52. Maybe I'll just calculate it. So A union B union C is equals to, so it will be nothing but 10 plus 20 plus 30. PIE. PIE is nothing but principle of inclusion exclusion. So A and B unit C is 10 plus 20 plus 30 minus of A intersection B, which is 4, minus of B intersection C, which is 5, minus of A intersection C, which is 6, and then adding back A intersection B intersection C, which is 7. So what does this leave us with? This is equals to 10 plus 20 plus 30 is 60. So 60 plus 7 is 67, 61, and this will be 56, and this is 52. So yeah, KS is already written. The answer is 52. So yeah, KS, your answer is correct. It's up to 52. Straightforward question. Let's just move on. Now, the seventh question is asking a basketball team has 7 players, each having distinct names. Every player has a jersey with their names on the back of it. If the jerseys are lying in the changing room turned inside out, how many ways can the players wear them so that no one wears a jersey of their name? So it's just a simple question. It's just asking there are 7 players and there are 7 jerseys. So each player generally has one jersey associated with them. But in how many ways can the players wear the jersey such that no player gets his or her own jersey? Right. So it's nothing but, as you can see, a straightforward question of dearrangements. So, so the answer is, so we just need to find the rearrangements or derangements. The number of derangements for 7 people. So number of derangements is generally is given by the formula, like as you guys might remember, it's like 7c0 times 7 factorial minus 7c1 times uh, 6 factorial. This is already done in the lecture. I'm just discussing this orally. So 7c0 times 7 factorial minus 7c1 times 6 factorial. Like it's also principal inclusion exclusion only. Like total number of ways of getting jersey 7 factorial. And then one player, I need to find number of ways in which no player gets his or her own jersey. So I'll subtract first of all the ways in which one player exactly one, at least one player gets his or her own jersey. So it will be 7c1 times 6 factorial because remaining jerseys can be commuted in any ways. And then I'll add 7c2 times 5 factorial minus 7c3 times 4 factorial and like so on. And this comes out to like nth dearrangement number comes out to approximately like 7 factorial, like n factorial times 1 by e. This must have been discussed in the lecture also. So this is equals to like 7 factorial times. Like you can generally do an approximation. So it generally approximates to 7 factorial times 1 by e approximately. So its value like you can do this approximation also, and its value actually comes out to like I think 1854. Or at least this, the value of this approximation at least comes out to 1854. So you guys can check. You guys can also find out the actual value by just putting like the finding all that calculation, which is like 7 factorial minus 7c1 times 6 factorial plus 7c2 times 5 factorial and so on. So that way you can get actual value. But if you just need to find an approximation, then I guess this is sufficient that 7 factorial times 1 by e is equals to 1854. So suppose this was a multiple types question, so you will just mark the closest value to 1854. Question. So in a class of 120 students, 67 students like mathematics and 86 students like physics, while 53 like both the subjects. And now we need to find what is the total number of students who like neither of the two subjects. So this is again a straightforward set theory question. I'll just write it down. Okay. So let's say M is the set of people, set of students like maths, and P is, oh, maybe it's a string spelling error. Yeah. a set of students like physics, right? So what do I know? Uh, I know that the class consists of 120 students, and like there can be some students who like only maths, some students who like only physics, some students might like both maths and physics, and some students might not like anything at all. So I need to find actually that number who like neither of the two subjects, who don't like maths as well as physics. So for that, it's a straightforward question. And maybe I can denote by U the set of all students. This is the universal set. So what we can say here is that, so okay, Aditya has written the answer as 26. So I think Aditya, the answer is actually 20 and not 26. So maybe I'll just discuss the solution and you can figure out how is this the case. Like this is something where you don't even need, I think you don't even need to write the formulas. You can just do this using Venn diagrams also, but nevertheless, let's just discuss it. So there are 67 students who like maths and 86 students who like physics, while 53 like both the subjects. So number of students who like exactly one of maths or physics. Yeah, Aditya, yes, answer is 20. Correct. Your answer is correct. So I'll just discuss how is it calculated. So first of all, let's just try to find out number of students who like exactly one of maths or physics. I have been given the students. So maybe like what I'm trying to do is let's see the universe set. So there are 120 students. I can partition the students into students who don't like any of the subjects, who like exactly zero subjects, which is the number which I need to find, who like neither of the two subjects, and the number of students who like exactly one subject, who like either maths or physics, and I don't know that value. And I also can separate it like the third component will be the number of students who like both the subjects, which I've been given as 53, right? So basically what I know in my solution is what I know already is like the total number of students is 120 students. And so there are some students who like exactly zero subjects, who like exactly one subject, and who like exactly two subjects. So I know there are 53 students who like exactly two subjects. And now I'm trying to find out number of students who like exactly one subject, exactly one of maths or physics. So how can I find this out? So there are 67 students who like maths and 86 students who like physics. So and while 53 who like both. So how many students are there who like exactly one of the subject? It will be nothing but 67, like number of students who like maths plus number of students who like physics minus the number of students who like both. So get you guys, why will this be the case? So I need to find the students who like exactly one of maths or physics. So this can be thought of in inclusion exclusion terms. So there will be people who like maths and there will be people who like physics in this term. But in that case, I would have counted the people who like both of these subjects twice, right? Okay, maybe the answer will be like two times this. So is this now? I think this expression is correct. So is this clear? So this this m plus p just gives the number of students who like maths plus number of students who give physics. From these, I'll need to subtract the number of students who like both or maths or physics, who like both maths and physics. And by that, I'll just get the number of students who like at least one of maths or physics. But I want exactly one. So I'll subtract this number twice. You can see this using Venn diagram also, like suppose there is a Venn diagram of sets M and P. So to obtain the regions, like the region which corresponds to like exactly one of maths or physics will just be the region of M union P minus M intersection P. So M union P will be given by um, M union P will be given by M plus P minus M intersection P, and maybe I'll just write it down that way also, is equals to M union P minus M intersection P, which will then be equals to this. So is this clear? So number of students who like exactly one of maths or physics will just be the students. M union P will give me who like exactly at least one of maths or physics. So this M union P will be nothing but the number of students who like at least one of maths or physics. And from that, I'll subtract the students who like exactly two. M intersection P is just who like both of the set, both of the students. So this will be the value who like exactly one, right? Because this is at least one and this is exactly two. So at least one minus exactly two will be exactly one only. So putting the value of M union P as M plus P minus M intersection P, and I get one more M intersection P from here. So that I'll get this twice M plus P minus twice of M intersection P. So I hope I'm clear. So M plus P will be like 67 plus 86. But even if you guys are getting confused, I think you can draw the Venn diagram for it and it will be pretty easy. Like by typing it out, it may seem confusing, but intuitively it's a very simple expression which I'm writing. Minus 2 times the M intersection P is just 53, since there are 53 students who like both. It will be 53, which will come out to 67 plus 86 minus 106. So it will be 47, I believe. Yeah. So number of students who like exactly one of maths or physics will be 47. So now I know my universe set is this U. So I know that this U, the total number of students is nothing but number of students like neither maths or physics plus number of students like exactly one. Or maybe I just write because number I'm using the this mod symbol already, so this will already account for number. So students who like neither maths or physics, size of that set, plus students who like exactly one, plus students who like both. Right. So this is the value which I need to find, right? Students who like neither maths or physics. What's the total number of students who like neither of the two subjects? This is the value which I need to find. Who like exactly one, the value calculated as 47, and who like both, we are given it as 53. And the size of U is also given as 120. Just putting these values in the equation, I get like 120 is equals to this value, which is the desired value, plus students who like exactly one will be given by this 47. Then who like both will be given to us as 53. So there are multiple ways of calculating this answer. So I've just given this one way. Maybe you can find another way to calculate it using Venn diagram. And all the ways are fine. They'll all reach the same answer only. So this is the equation which I get. And this 47 plus 53 will give me 100. So 120 minus 100 will give us me 20 only. From this I get it's 120. This is my final answer. So I hope it's clear. And Aditya, you gave the case your answer was correct. The answer was 20 only. So Aditya, you gave the answer is 26. So have you found out the mistake in your solution? And do you understand this correct approach also? Okay, cool. You have understood. Nice. So like maybe there is another way to solve this and all the ways are fine, or we'll reach the same answer only. Oh, this is not 120, this is just 20. Sorry. Yeah. So now I think we can move on to ninth question. So ninth question is nothing, but it's just asking in how many ways can five tigers, five lions, and five elements march past in the same row such that no consecutive five animals of the same family are together. So again, it's a question based on principle of inclusion, exclusion, and what it's asking us is that there are five tigers, five lions, and five elements. All are moving in a line. Let's say march past is in a line. So such that no consecutive five animals of the same family are together. So what we want is neither the all five tigers should not be together, all five lions should not be together, and all five elephants should not also not be together, right? Okay. So for this also we'll try to use inclusion exclusion. So first of all, let's just see total number of ways. So what will be the actually the total number of ways for these like uh, five tigers, five lions, and five elements to march past. So it will be nothing but there are so like without any of these restrictions. Like if these restrictions are not there, then how in how many ways can five tigers, five lions, and five elements march past? So it will be nothing but just number of ways of arranging like these 15 objects, like five tigers, five lions, and five objects are total 15, where these five are of the same type, these five are of the same type, and these five are of the same type. So five are tigers, five are lions, five are elephants. So it will be nothing but like 15 factorial divided by like five. Like we know from multinomial theorem, right? Because there are like similar five objects of one type, five of another, and five of another type. So we'll need to divide by 5 factorial because of this, 5 factorial because of this, and 5 factorial because of this. So it will be like 5 factorial divided by 5 factorial cube. So I hope this makes sense. This is the actual total number of ways, but we don't need this. We need to find actually the number of ways such that no consecutive animals of 5 family are together. So number of ways such that this are together will be nothing but like from this total number of ways 15 factorial 5 factorial cube. So from this what I need to subtract is okay ks your answer is almost correct except the fact you have written in chat some answer using Inclusion exclusion, but you have not accounted for like these five tigers are of the same type, five lions are of the same type, five elephants are of the same type. So you need to account for this fact also. Like total number of ways will be not 15 factorial, but 15 factorial by 5 factorial cube. So maybe you can, I'll just explain my answer and you can understand and ask out after this. So, so total number of ways. So what we want is, uh, we want these five tigers to not be together, these five as well as these five lions to not be together, and these five elephants to not be together, right? So from these total number of ways, and again using inclusion exclusion, I'll just first subtract the ways minus number of ways which tigers are not together minus So tigers are not together, as well as I also want lions are not together. And similarly, I also want elephants to not be together. These are total number of ways. I don't want tigers to be together. I don't want lions to be together, and I don't want elephants to be together. So I subtract these three values, but while subtracting these three values, I'll be subtracting a little bit extra, which will be like number of ways in which tigers and lions are not together, like taken pairwise, plus number of ways in which uh, lions and elephants are not together, plus number of ways in which tigers and elephants are not together. And while adding this extra, I'll be subtracting that case where like number of ways in which lions, tigers. Okay, I think I made a bit of a mistake here, first of all. So total number of ways will be like this. So from this, what I need to subtract is like this is the total number of ways, and I actually need the number of ways such that no consecutive five animals are together, right? So from total number of ways, I'll actually be reducing the number of ways in which they are together. I hope I'm making sense. So from this 15 factorial by 5 factorial cube, I'll be reducing the number of ways in which tigers are actually together. Because this will like this 15 factorial minus this number will correspond to number of ways in which tigers are not together. And that is what I precisely want to calculate. Similarly, lions are together and elephants are together, in which tigers and elephants are together. Like they are not together with each other, but like this means that tigers are together amongst themselves, like the five tigers are together and the five lions are together. But this doesn't necessarily mean that these five tigers and five lions should be all be together with each other. Similarly, this, and I just remove these knots too. Or maybe a better way to write it is in which tigers together, comma lions are together. This way there is no confusion. So number of ways in which tigers are together, comma lions are together, and number of ways in which lions are together and elephants are together. Just writing it down in a different manner. So after you read this doc, you don't get any confusion. Number of ways in which tigers are together, elephants are together. And then I'll subtract number of ways in which lions are together, tigers are together, comma, elephants are together. Okay, so this will be the actual answer. So total number of ways. So actually, I want none of the five animals to be consecutive to each other. Like none of these three types to be consecutive. Like these five tigers should not be together. These five lions should not be together, and these five elephants should not be together. So from total number of ways, I'll subtract number of ways in which these tigers are together. Similarly, in which lions are together and elephants are together. And while doing this, I'll subtract it this ways in which tigers are together and lions are together. And similarly, in which lions are together and elephants are together, and so on. So I just applied the principle of inclusion exclusion. Now I'll try to calculate these terms individually. So let's just see like number of ways in which tigers are together. So to calculate this, what we can think of is suppose now the five tigers are together and the five lions and five elephants can be anywhere. So if these five tigers are together and like any permutation of these five tigers is not different since these five tigers are identical objects, right? That's why we were dividing by 5 factorial in the first place. So in fact, what we can see is we can think of this as we are being given five elephants, five lions, and a set of 5 tigers, which will always come together. So in fact, what we can think of it as we are given 11 objects, like 5 lions, 5 elephants, and another object which corresponds to those 5 tigers. So we are given 11 objects, out of which 5 lions are of the same type and 5 elephants are of the same type. So I just need to arrange 11 objects in such a way, arrange 11 objects in which 5 are one type, 5 are of second type. Right? And third type is the set of 5 tigers, which is just one object. So this will just be like 11 factorial divided by like 5 factorial square. 5 factorial corresponding to lions and 5 factorial corresponding to elephants. I hope this calculation is clear. This 11 comes out from 5 lions, 5 elephants, so 5 plus 5, 10, and one set of 5 tigers, which will always be together. So this comes out to 11 factorial by 5 factorial squared. So similarly, I hope this is clear. And then this number of ways in which lions are together will also come out to this value only. And this will also come out in which elephants are together will also come out to this value. So now calculating this value in which tigers are together and lions are together. So now to calculate this value, number of ways in which tigers are together, lions are together. So in this, what we are doing, 5 tigers are together and these 5 lions are together. So these can again be taken as 1 sets each. So and now 5 elephants can be permuted in any ways. So we are we are being given a set. We are being given 7 objects basically, like these 5 elephants. Then this set of lions is one element. This set of tigers is another element. So we are being given 7 objects, out of which 5 elephants. These 5 objects are of the same type. So now we want to arrange these. So there will be total 7 elements. 7 factorial divided by these, since 5 elephants are of the same type. So we'll just divide by 5 factorial corresponding to these elements. And as you can see, since similar, this similar value will come out to all of these terms. This term will be 7 factorial by 5 factorial. This will also be that. And this will also correspond to that. So nothing too fancy. Now we want this sort of term we want to calculate this sort of term. Number of ways in which lions are together, tigers are together, and elephants are together. So now all of these can be considered as one set, right? Like one set each. So elephants correspond to one set, tigers correspond to one set, lions correspond to one set. So we are being given like 3 objects. So 3 objects and all 3 are different to each other, since set of lions is different to set of tigers, which is different to set of elephants. So these can just be arranged in 3 factorial ways. Right? Am I making sense? So putting in these values, what we get is values. Maybe I can shift the margin down. You get answer equals to 15 factorial. Maybe I'll just write it down in next page only, since otherwise it can cause confusion. Factorial by 5 factorial cube. Maybe I'll just putting in that formula again and now substituting the values. So this number of ways in which tigers are together will be replaced by 11 factorial by 5 factorial square. This will also be replaced. This will also be replaced. So these 3 can be replaced together. Minus 3 times this value. And now this number of elephants in which tigers are together, lions are together, and like these 3 values can be replaced by 7 factorial by 5 factorial. So plus 3 times this 7 factorial by 5 factorial. And now this last value in which lions, tigers, and elephants are together can be replaced by just 3 factorial. Doing this. Okay, so this is the final answer which we get. And what does this calculate to? Do I have the answer for this? Okay, so I don't have the answers for this, but this will be the correct answer. So 15 factorial by 5 factorial cube minus 3 times 11 factorial by 5 factorial square plus 3 times 10 factorial by 5 factorial minus 3 factorial. So Aditya and KS, is it like, do you guys understand it now? KS, initially you wrote answers similar to this, but not quite similar. So do you understand your mistake now? Okay, cool. You understand the mistake. So let's move on to like the last question then. Last question for the day, which is the 10th question. So it's a straightforward question again on like the dearrangements. So what it's saying is, so we are being given like Greek alphabets, alpha, beta, gamma, delta, like up to n. Like suppose there are some n alphabets. I don't know what the nth alphabet in Greek is, but let's just say we are given some n alphabets, and we know that there are this much possible dearrangements where these appear in the first six positions. So first of all, like what is a derangement, guys? Derangement is an arrangement in which no element is at its original position, right? So that is the basic definition of a derangement. So for this list, suppose instead of this, we were given A, B, C, D, A, B, C, D, E up to like, let's say Z. So a derangement for that will be like an arrangement of these terms in which A is not at first position, B is not at second position, C is not at third position, and so on. Similarly, here, like a derangement will correspond to uh, a permutation where alpha is not at first position, beta is not at second position, gamma is not at third, delta is not at fourth. So yeah, so this is what a derangement will correspond to. Now, out of those derangements, it's saying that 4931310 derangements are there. This is not the total number of derangements, but the derangements where alpha, beta, gamma, delta, epsilon, and I don't know what this last term is. They appear in the first six positions. So one important thing to note is that these alpha, beta, gamma, delta, epsilon, and this term, these are the first six uh, Greek alphabets. Okay. Like if we think of it as like A, B, C, D, E, then these are A, B, C, D, E, F of the Greek alphabets. Okay. And it's saying that there are 4913110 rearrangements where these appear in the first six positions itself. So actually like derangements are terms where like alpha does not come at first position, beta does not come at second, gamma does not come at third, and so on. But out of those derangements, we are considering those in which even though like alpha does not come in at the first position, it comes in the first six positions. Similarly, beta also does not come at second position, but it comes at like, let's say first or third or fourth or fifth or sixth position, and so on. So it's just saying that so basically what you can think of it is that these first six positions, these are the first six Greek alphabets, and they are deranged between these first six positions only. So does it make sense what I'm saying? So what I'm saying is that total derangements can be much larger than this. So total number of derangements, what can be the case? Like alpha can go to nth position also, beta can go to n minus 1th position also. But what we are saying, there are 4913110 derangements in which these first six Greek alphabets are deranged in their first six positions only. So basically you can think of this number as the number of derangements where these first six alphabets are deranged among themselves, and then the remaining n minus 6 alphabets will be deranged among themselves. So am I making sense, guys? I hope I'm making sense. If not, you can ask me in chat. So what this question is asking is that these are the first six Greek alphabets and they appear in the first six positions, but they are deranged, so they don't actually appear at their or at the original position. So this number is can be thought of as just these first six alphabets appearing in the first six positions, being deranged in the first six positions, and the remaining n minus six alphabets are deranged in the remaining n minus six positions. So the given number of derangements can be thought of as the number of derangements where like alphabets are deranged amongst themselves and the remaining n minus 6 alphabets are deranged amongst themselves. So I'm clear. So note that in actual total number of derangements, like alpha can go to nth position also, but we are restricting it to alpha being in the first six positions and similarly beta in the first six positions and so on. So these like the first six terms and the remaining n minus six terms can be thought of as being independent of each other, right? The first six alphabets are being deranged among themselves and the remaining are being deranged amongst themselves. So since these two can be thought of as being independent of each other, so this 491310 as these two derangements are independent of each other, means total number of such derangements is equals to nothing but like since these two are independent, like 6 and n minus 6 are independent, so it can just be thought of as a product of these two derangements. Like this the total number of such possible derangements is nothing but the number of derangement between first six alphabets times the number of derangement between the last n minus 6 alphabet. Number of derangements between six alphabets into number of derangements between n minus 6 alphabets. Yes, so yeah, this is the basic idea, and I hope it's clear like why I'm writing this product, because these are like these n minus 6 are deranged among themselves and 6 are deranged among themselves. So like these are independent of each other. So the total number of such derangements is just the product of these two. And this total number is given by 491310. So this is nothing but like number of derangement between six alphabets. So this is like if we denote like the derangement number as D. So D of 6 is just number of derangement between six alphabets times D of n minus 6. Right. And we have already seen in lectures like what's the value of like D of n? It can be approximately written as like n factorial upon E. So like you can find out exactly also D of 6 you can actually find out using the formula of derangement like 60 times 6 factorial minus 61 times 5 factorial plus 62 times 4 factorial and so on. You can find the exact value also, but I guess it works if you just do it approximately as well. Since the questions are generally MCQs, so in MCQs, you can give the value like you can give the answer as the closest one. So yeah. So 491310 is nothing but like 6 factorial times. And we need to just find the in the question the value of n. So this 6 factorial can be written as 6 factorial. This d of 6 can be written as 6 factorial times 1 by e. And similarly, this d of n minus 6 can be written as n minus 6 factorial uh, into 1 by e to 1 by e. So like, yeah, this is a very tedious calculation, but from this you will just get like you will get like n minus the value of n minus 6 factorial as something. and that something will correspond to approximately. I'm just hand waving at this. Maybe you can try it out using calculator, so it's easier for you guys. But from this, you will get that n minus 6 factorial is equals to uh, 7 factorial, I think. Yeah. So like from this equation, like 4913106 factorial times 1 by e times 1 by e and n minus 6 factorial. So to find n minus 6 factorial, you will take all of this stuff to the this side. And while calculating that, you'll just see that it will be approximately equals to 7 factorial. Like since there is an approximation of 1 by e here, so I'm just doing it approximately. So this will actually be like approx. So since n minus 6 factorial is equal to 7 factorial, so this will imply that n minus 6 is 7, so n is 13. Is the correct answer. Like I have just done a bit of hand waving here that from this you will get this, but you can verify these calculations using a calculator by yourself, and it won't be too difficult. So generally, like why I'm doing it approximately, because like calculating the actual dearrangements is quite tedious, since you need like those a lot of terms like 61 times 5 factorial, 62 times 4 factorial, and their addition, subtraction, so on. But you can approximately write it as this also, 6 factorial times 1 by e. And this saves us a lot of time, even though it introduces some approximation factor. But I guess like saving time is much more important than like saving on some small value. So from this, we'll get n equals to 13. So you can trust me and try to do this calculation yourself, and you will obtain the same answer. So I hope it's clear to you guys. So if you have any doubt regarding today's session, maybe we can discuss it quickly since we are running out of time. So, or if you don't have any doubts, then maybe we can close the session for today. Okay, since no one is typing in the chat, I'll just assume that none of you have any doubts for today's session. So yeah, I hope you guys enjoyed today's session, and we'll be meeting tomorrow. We'll be meeting next Tuesday at the same time, 6 to 8. So hope to see you guys there also. So thank you for attending today. So goodbye, guys. I'm just closing the recording and screen, and you can exit. Bye bye.